So, ladies and gentlemen, considering the what we end up seeing in the previous video here, it would seem that we need to motivate a new definition for congruence, or rather, maybe not necessarily a new definition, but an extension of one here. So notice how we have this idea that two polygons are congruent. So now this definition of congruence here is going to apply to polygons. So it's a slightly different version here. If and only if they have, so not only do we need to have congruent sides, we also need to have congruent angles, and there's this idea of matching here, this correspondence here. So our definition for congruent polygons here is going to be, we're going to adopt this definition here. If and only if they have congruent corresponding sides and congruent corresponding angles. Notice how in this situation here, you want to have everything. So you need to make sure everything corresponds and they're also congruent here. So not only do you have to have actual pairs of objects here, you need to make sure they're sort of matching with one another in the same relative positions in your figures here. So not only are the congruent angles are going to exist here, but also the congruent sides are going to exist here as well. So we're going to keep this in mind. Now, I realize it's kind of weird that we have congruent here, but notice that congruent corresponding sides, that's actually well defined here because we know what it means for sides to be congruent here. And also segments, and we've defined segment congruence here. Same thing with angles. We defined angle congruence here as well. So even though technically we seem to have used this definition, a term in its own definition here, this is actually okay because this actually refers to something we've looked at in the past. Now, this means here, ladies and gentlemen, that if I want to show that two polygons are congruent, according to the definition, I have to show every pair. I have to show every pair of sides and every pair of angles. So for an n-sided polygon here, right, I need to show n pairs of sides, n pairs of congruent corresponding sides, and n pairs of congruent corresponding angles. So that's two n pairs of things I have to prove. So even when we have the smallest possible value of n for a polygon, 3, the humble triangle, that's 2 times 3, that's 6 pairs of things I have to show. That's a lot. I'm hoping there are ways of doing this that doesn't have to, that we don't have to show all 6 pairs of things. Can we go lower than 6 pairs? So, considering what you know about triangles already, you might be able to say, okay, well, maybe we don't need all 3 pairs of angles, right? If you have 2 pairs of angles here, the third pair has to be congruent because if you have 2 x's and 2 y's, you know that the sum of the interior angles of a triangle is sum to 180. So that means the remaining angle has to be the same thing because you're subtracting equals from equals. So you technically only need 5 pairs of things, okay? Right? You can reduce it to 5. And you can actually keep going down here. So it's, as it turns out, for our simple friends, the triangles here, there are actually 3 ways to show that the triangles are indeed congruent here. And these are all going to be postulates that we're going to adopt here. The first of these postulates is what is known here as side, side, side. And this is probably the most straightforward of the postulates here. So we'll call this the SSS postulate. So you actually don't need to call this side, side, side. You don't have to write this out here because this is something that we accept. This is a accepted name. You can actually say by side, side, side. So 2 triangles are congruent if and only if they have 3 pairs of congruent corresponding sides. So notice how you have congruent corresponding sides here. BC matches the EF. That's 1 pair. AB matches with DE, that's 2 pairs, and AC matches with DF, that's 3 pairs. So you need 3 pairs of congruent corresponding sides for this here. Okay, so this is side, side, side. This is one postulate here. Another postulate we can take a look at is what is known as side, angle, side. So we can say that two triangles are congruent if and only if they have 2 pairs of congruent corresponding sides and their included angle congruent here. So notice when I say included angle, take a look at the picture here. I've got 2 pairs of congruent sides, so BC and EF match, AB and DE match. But in this situation here, we're going to be looking at something a little bit differently. Notice how in this situation here, this is the included angle here. So we call this included. And this is also the included angle here. So the reason we call this the included angle here is if you consider this, take a look at what's going on here. Notice how we can have, say we have side A, we have side B, right? Or rather, side alpha, side beta. We've got 2 alphas and 2 betas here. If you look at alpha and beta, they actually form the side of an angle here. And we see that this angle B is sandwiched in between the pair of sides here. So I got, 1 alpha and 1 beta here. I got 1 alpha and 1 beta here. And the angle that's sandwiched in between, we refer to that as an included angle here. So it's trapped in between the sides here. So we say it's an included angle here. So this here is an included angle in both situations. So notice how it's side, angle, side here. To represent the fact that the angle is included between the sides here, we say side, angle, side. So it's SAS here, okay? So don't rearrange the letters, please. In this situation, side, angle, side refers to the fact that the angle is sandwiched in between the 2 sides here, okay? And the third of the major postulates that we're going to be looking at here is basically sort of the reverse of side, angle, side here. We're going to refer to this as what is known as angle, side, angle. So this here is the angle side angle postulate here. We can say that two triangles are congruent if and only if they have two pairs of congruent corresponding angles and they're included side congruent. So notice here, I've got one pair of angles, one here, B and E. I've got another pair, C and F. And again, we can see that there's a side that's in between here, right? If you look at the two sides in each of the triangles here, they have a common segment. And that common segment here is our included side. And this is also an included side as well. So just like with side angle side here, we want to sandwich we're going to sandwich the side between the angles here, as opposed to with side angle side, we sandwich the angle between the sides, okay? Now, I realize here that it seems kind of weird for me to introduce the postulates and not actually explain why they work. I mean, technically I don't have to explain why they work because they're postulates, we can accept them to be true. But I want to appeal to your intuition. But in order to do that, I kind of need technology here that I can't really show under this camera here. So you'll have to tune in to the lesson that I do online, the live lesson, where I can actually do some sort of I can use the computer to show you that to appeal to your intuition that these three postulates here actually work. That side angle side, side side side, and angle side angle all should work here. So join me there, and we'll see what happens.